So what's the plan for today? So two completely different, well, two related things, but conceptually different things. So we'll first talk about, so the lecture today and on Friday is really going over the scans that are most commonly done at the MRI center. So these are rapid functional MRI scans using Echo-Planar Imaging and undersampling. And so we'll talk about that today and on Friday. So starting off with Echo-Planar Imaging. So this is so the basic idea of Echo-Planar Imaging is very old. It actually dates back to like 1990 or something like that, when people first thought about doing it. And so when we normally think of the pulse sequences that we've shown, especially the slow versions of them, you do some pulse, and then that causes, an FID, and then maybe you turn some gradients on, or maybe do another pulse and get an echo, and then maybe if you're doing spin echo, you would do like a 180, and then that amount of time later you get an echo, and then you record that echo. But where is the biggest signal? It's right here, right at the very beginning. That's the biggest signal by far. And so the idea of Echo-Planar Imaging, and so in this case you just basically record, in slow spin echo or slow gradient echo, you just record one echo. And then you have this idea of echo trains. You could do multiple 180s or multiple gradient echoes, but it's still not fully taking advantage of all this good signal here. And so what Echo-Planar Imaging is, it's very simple. It's just, let's just record all of the echoes that we need for a whole slice from one FID. So what does that look like? So that just looks like we basically, if you imagine, here's a slightly bigger picture of an FID. So here's the oscillations that come out, and what does that take? That takes like about, say, 50 milliseconds total. And so what's Echo-Planar Imaging? Well, let's just record all of the echoes we need for one slice during that time. And so normally I was drawing pictures that look like, the FID like this, and then a gradient echo coming off of it like that. So like you do an RF pulse, and then you turn the gradient on negative, and then turn it on positive like that, and then you get an echo, and you record that echo. Why don't we just jam all of those echoes into a single FID? So this is an FID with no gradients on. And so what we could do is just virtually as soon as the FID starts, immediately slam the gradient on all the way, and then turn the gradient reverse the other way, and then slam it on the other way, and then turn it reverse the other way, and slam it on the other way. So basically you're getting and each one of these, is making an echo, like that. So you're basically essentially collecting all of the echoes, like 64 echoes that we need in order to collect all the data, all the case-based data for one slice. So that's just in words what Echo-Planar Imaging is. And so now let's just go over the details of how we actually collect all the echoes needed for one slice. So like 64 or 128 echoes. So to start, the first thing we do is the fat saturation. Okay, so what is that? So the idea is that we want to kill the signal. So fat saturation, we want to kill the signal coming from fat. And so the signal So why is that a problem? Well, the problem is that the fat resonates at a slightly different, because of the chemistry of the protons in fat, it resonates at a slightly different frequency. And that difference in frequency is going to be interpreted as a spatial shift, because the gradient causes a difference in frequency, which causes these phase wraps. But fat can cause these phase wraps too, because it resonates at a different frequency, which means the phase is sort of getting ahead as if the gradient was on. And so basically you'll misinterpret. We'll go over the equations for why you get a spatial shift, but basically if you get a different resonant frequency that causes a phase problem, that's actually going to cause a spatial shift. And so what will happen is you'll get a little band of the fat. You have a little bit of fat underneath your skin on your skull. You'll see that shifted over, and it will, on one side it'll be sticking out in the air, and the other side it'll go into the brain. And obviously that's going to mess up your image. And so for that reason, we do a fat saturation pulse. And this is a 90-degree pulse. And the idea is we sort of tip all the magnetization to transfer so there's no longitudinal. Now, that's going to make a signal. And so we have to get rid of that signal somehow. And so we have to, so this is done before virtually all fMRI pulse sequences. So the first thing we have to do is select a slice, but when we do our FAT-SAT, the frequency that we use, so it's the frequency is offset, because the frequency of water, which is most protons, is here, and then the frequency of fat is a little off to the side. So basically we do an RF pulse that's offset in frequency so that we only hit the fat protons. But we still have to do a slice select and then fix the slice select in order to just do that for the current slice we're working on. And then what do we do? So that if this is RF in, so RF in, and then the gradients Y, X, RF out. So we will still have a transverse. We won't have any longitudinal. We will have gotten rid of the longitudinal so that when we do another 90, there's nothing to flip. But there's still some transverse there, and so we have to slam that transverse. And so what we do is we do a crusher here to sort of, on that gradient, to crush fat. So crush the fat signal. So there's a transverse magnetization signal that we don't want to get into our recording. So we sort of wrap it up into 512 stripes, which is almost no signal. So that's the fat crusher. Then we're ready to actually do, and that doesn't take very long, because we make a signal, but then we can quickly hammer it to make it go away. And then we do our water 90. So this is another 90. This is water. So that means, so that one is set up for the frequency of water. So here's another slice select, and we'll now do the flip that's going to generate the signal that we're going to use for the whole rest of the sequence. So then while that's happening, while we're sort of like fixing up the Z magnetization. So let me just draw over on this side. We'll put a big K space. So this is, K X going in that direction, Ky going in that direction. So the first thing, we'll just start here. So the first thing we do is we end up at point A. So when we do our slice select, we come out of the board, and then we do the slice select fixer. It brings us back into the board, and then that starts us at the middle at point A. So that's point A right there. At the middle of K space, no stripes, all the spin phase lined up because of the 90 RF pulse. Okay, and then even while we're in the midst of doing that, because we want to save time, we go to the far left side of K space and the bottom of K space. And so how do we do that? So we turn on both gradients, the X and Y gradients at the same time. And so the Y gradient, if you turn it on negatively, it's going to wrap up spin phase, horizontal spin phase stripes. And the X gradient is going to wrap up vertical. If you put those both together, you get sort of diagonal stripes. And so you'll head down to the corner of K space like that. And so then so by the time you get down there, you're at point B. To save time, those are usually done at the same time, but you can sort of conceptually think of them as different. And so then we end up at point B. So now we're down here. And then we reverse this gradient, and after we've essentially done the exact reverse of that gradient like that, we will go back across K space. So we'll go back across K space and get an echo. So at this point, at point C is when the echo will occur. So at point C, now it's going to be a small echo because we've put on two gradients and we've got 64 stripes all wrapped up, also known as dephasing the signal. And so it's going to be a very small, the outer part of K space is going to be a very small signal. So there will have been, let's put in these other signals. So there will have been a really big signal coming out of here like this. But as soon as we slam on those gradients, that will squish the signal down to almost nothing. And there will have been a signal right here that was also quite big. But as soon as we turn that gradient on, it'll squish that one. So that one would have gone on for quite a long time if we hadn't turned this thing on here to squish it. Okay, so now we're at the middle of K space, and then we just continue, leave it on for the same amount of time again. It's supposed to be the same, like that. And that runs us all the way over to this side of K space. So now we're we were at C over here, and then we're at D over here. So that's just like we did before. You just go somewhere in KY and then read out a line of data. So we read out like a line of 64, 128 points. But now what we do is turn the phasing code gradient on. So remember, we haven't, aside from sort of going to the bottom of K space, we haven't really turned the phasing code gradient on. So this one is, this guy is slice. This is phase, and this is readout. So we haven't turned the phase encode gradient on, but what we do now is at this point, right where we're crossing 0, we turn on a blip. So that's called a blip. So that's just like a, why do they call it a blip? Like if you turn, so what's actually making noise? Like if you listen to one of these sequences, what you hear is like a beep, beep, beep. You hear this really high-pitched sound, like 1,000 hertz. And the reason for that is this looks like 1,000 hertz sine wave. It's going up and down 1,000 times a second. And that's a really big signal going in, really big current going into the gradient coil. And the gradient coil is it generates a magnetic field, and that magnetic field reacts with the magnetic field, the B0, and it causes the gradient coil to wobble back and forth. And that's what's actually making the noise, that high-pitch beep that you hear. But if you, and we'll take a trip over to the MRI center and just sort of turn on the magnet so you can hear some of these things. If you just turn that off, turn that gradient off and just listen to that, then you just hear the blips. And the blips are little, they're just little tiny sounds because it's not much of a gradient. But it's a positive gradient, and so what does that do? It's in the midst of this other gradient sort of still being on, and so what it causes the position in k-space to kind of like loop around, and then you get to point E. So it just moves you up just a little bit in k-space. It's not very big, and so now we're at point E. So and now we're ready to record another line of k-space, but we're at the right side of k-space, and so we have to turn a negative gradient on. And so there's our negative gradient, like that. And there'll be an echo in the middle of that one. Another echo, slightly bigger. And by the time we get all the way across there, we'll be at point F. So here's point F. And so we'll go all the way across, record another set of data points, and then we get to point F. And then just keep doing that. So what will happen is we'll do that, 64 times. Okay, so let's just say we cut all those out of there. And then finally, so we keep going back and forth. So there'll be another blip right here. There's another one, and there'll be another one right here, and another one, right here, etc. So every time we cross 0 on the x gradient, there's another blip to take us up. So basically, it'll just go back and forth like that until eventually we get to the center of k-space. And so when we hit the center of k-space, then we'll get a big echo. And so let's cut that off, and then we take up. So we're going back and forth like that, and say that's the center of k-space. So this is the center of k-space, and so that point will be at the center. As we go through the center of k-space, that point will be EFG. So now we're at point G over here, and so that's when we get our biggest echo. So if you look down here, this will be an actual big echo. It'll be bigger than these because these were more dephased because they were at higher k-space. So one of the things you notice, there's a whole bunch of TEs here. So this was the fat one, and this was the water one, and so the fat one we can ignore. But so that's a TE, and then that's a TE. They're all different. And then this is a TE. And this is the TE that if you look on the scanner console that you set, this is the TE you're setting. So this is the TE, effective, because that's the TE to go through center of K-space. And that's the one that most strongly affects, the low spatial frequencies are the ones that most strongly affect the overall contrast in the image. But we're still not done yet, and so now we have to sort of collect the whole rest of K-space, sloppily like that, okay? And so by the time, we eventually get to maybe G, so point H, so we're finally recorded all that. So there'll be, another gap where we record the whole rest of K-space. And then finally, so now here's the last of it for one slice. And so this is basically, one slice here. But there's other slices to do. So one slice. So it's all the K-space data for one slice. And then what do? We do another slice. So this doesn't take very long. This only takes like, say, 60 milliseconds or something like that, or 50, 60 milliseconds, a very small amount of time. So now we have time to do another slice. Actually, all the other slices. So all the other slices. And so that's going to take more time. It's going to take however many slices you have times this amount of time. So we do all the other slices. Then finally we're back to do this slice again. And what is that time? That time might be only 1 second, especially if we're doing undersampling. And so we finally do the FATSAT and the water 90 for, so say that's the water 90. And so that's the TR, 90 degree water. So our TR is this time here, from here to here. And what is that? So our TR might be, for example, 1 to 2 seconds. So this means that we can record like 15 or 20 slices per second. So that we can essentially image the whole volume of the brain every second or two. So it's a kind of a sloppy imaging technique because we'll see that there's a lot of distortions in it. We'll try to explain why those distortions are there. It's a little complicated story to explain that. I'll do that next week. But the great advantage is that we can collect a whole volume of the brain in 1 second. And that's the only way that if you're trying to do functional MRI where you're looking at changes over time due to changes in blood oxygenation, which are caused by changes in activity, those changes are happening sort of second to second. And so we need to be able to record very quickly. So what was the reason? So this method is an old method. I mean, the very original one didn't have blips because the amplifiers weren't quite snappy enough. And so what they did in the original one was just turn the phasing code gradient on continuously, and what happens there is you'll do like a zigzag across K-space like that. But the problem with that is that the Fourier transform wants a regular grid, but that's okay. So what you can do is you can get the regular grid and then resample onto the grid. So you can resample those diagonal lines, interpolate them onto a grid, and then you can do your Fourier transform. A little bit of a little bit of a hassle, but that's a pretty straightforward thing to do. So that's the very original echo-planar imaging, was just turn the phase encode gradient on just a small level and just keep it on the whole time, and that will slowly advance you in the direction across K-space. Now they just do these little tiny blips. And what is the main reason for doing this? What is the main reason that made this possible? And it's mainly sort of improvements in amplifiers. So if you look at a transistor is like a multiplier. So you've got two things coming into the transistor and one thing coming out. And how does the transistor work? Well, you have a big current sort of flowing through the transistor this way, and then you have a little tiny current, on this other wire coming into the transistor, and that will essentially multiply this much bigger current. And so that's basically an amplifier. So we have this tiny signal here, and then that will be amplified into a giant copy of that signal. And if you use a transistor like that, there's limits on how much power you can run through the transistor. So it turns out there's another way to make the transistor work, which is just to make the transistor work as a switch, just an off-on switch. And it turns out if you do that, it's possible to run more current through the transistor, a lot more current through the transistor. And that's the way the amplifiers that we have now work. And that's why you can get a 1,000,000-watt amplifier into a little container like this big. It's water-cooled because it gets quite hot. But so the way the actual gradients work is they're switched. So what happens is if you want to make some kind of gradient waveform like that, like this, this is our gradient waveform. That's called, if you read a paper, gradient waveform. So say this is your gradient waveform. How does the amplifier actually make it? It makes it by switching the transistor on and then turning it off, and then switching it on again and turning it off, and switching it on again and turning it off. So that seems like that wouldn't be a good way to make a nice smooth curve, but it turns out because of the inductance in the coil, which is basically sort of effects on current that are due to magnetic fields generated by the current going through the coil when you change it, that will actually smooth out the output gradient waveform. And so, but what's actually happening down sort of deep in the bowels is these things are just switching like 100,000 times a second and just turning on and off. And that's called a Class D amplifier, and that's why you can make like an amplifier. So it's sort of simulating an analog signal with these little digital switchings. And so until that happened, it was hard to get enough power into the gradients to make them change this rapidly. It's particularly hard like when you have a little corner like that or like that. That's kind of hard on the gradients. So when that happened, when these amplifiers became, more readily available, like about 15 years ago, then everybody and their uncle started doing echo-planar imaging. Okay, so that's EPI. So any questions about EPI echo-planar? The echo-planar means like it's just like you're just doing one whole plane of K-space at once, just from a single 90. So you just do one 90-degree pulse, and then record 6,000, 5,000, 10,000 data points just from one RF pulse. So is it sort of clear? Any questions about sort of echo-planar imaging? Like very super fast? Yeah. You often do it in some of the other sequences. So it's not that, I didn't talk about it in other sequences, but it's not uncommon. It's not uncommon to do it. It's particularly important here just because it depends on like how much fat, what are you recording? If you're recording a muscle, maybe it doesn't have much fat in it. If you're recording an old person's muscle, more fat in it. So it's kind of variable. Or if you're recording some part of the stomach where there's a lot of fat, then it's going to cause more trouble. Here, the reason it causes trouble is because you've got this little layer of fat under the skin. And for a normal pulse sequence that is not, so one of the problems here is that these little blip gradients are really small. And so any B0 problem, like for instance due to the fat, because the fat is resonating at a different frequency, have more chance to mess things up because the ratio between the magnetic field offset and this little gradient is unfavorable. It's less of a problem here. You've got these giant gradients because these are like muscling things around, and so you don't have problems in the kx axis. But these little gradients are so small, and you're doing a long readout, like 50, 60 milliseconds of data, and so there's more chance for that to cause a problem. And what will happen, like I said, on one side it'll be okay, like the fat will be sort of sitting out in the air like that, but on the other side the fat is going to be moved inside the brain, like a little white stripe inside the brain, and then really mess it up. And you can you can just tick it off on the EPI and just see, just suddenly you'll see the fat will suddenly get brighter, and then you'll get this little sort of ghost. But it's often used in other sequences, so it's not just this one, but it's almost virtually always on here, just because we're almost always recording the brain. Okay. So we haven't talked about speeding this up even further, and so that's for Friday. So almost all the time people are doing something called multiband now, where you record multiple slices at once. And so we'll talk about that. That's like the ultimate speed up. So we'll talk about how that works. But in order to understand how that works, we have to understand about undersampling. And so this is, I didn't really understand this for a long time. There's a certain intuition about it that I can give you at the beginning, but it doesn't allow you to really understand it. And hopefully we'll go over the Fourier convolution theorem version of it, and perhaps that will be clearer. And it's related. There's many different ways that we can try to undersample. And what does undersample mean? It means I don't collect all of k-space. And some of the homework problems are exactly on this. Like, what happens if you just leave out half of the lines in k-space? What does it do to your image? So first, the somewhat garden path sort of intuition. And so the intuition is, if we've got multiple coils, we might be able to undersample. So here's a person smiling because they're liking being scanned. And if you've got a coil, if you have one coil over here, and then you have another coil, say, over here, there's the capacitor. It's got a capacitor in it. And you imagine this coil over here is going to pick up really good from, this part of the brain, and less from the other part. It'll pick up the whole brain, but it's going to have a little sort of bright spot because it picks up better, like from this part. Now imagine you've got a point, somewhere, say like right here, point X. It's obviously going to be, there's some spatial information here, so point X is going to be stronger in coil A than it is in coil B. And so somehow there's an intuition, there's some spatial information in the distribution of the coils, and you should somehow be able to use that to help you out when you're doing a reconstruction. And that's true. That's true, but it doesn't really sort of give you an idea what the actual mechanism is. So, but early on, if you look at the earlier papers on this, they're very hard to understand, and they didn't kind of unify the whole. There's many different ways of undersampling, and they all rely on what we're going to talk about on this side of the board. So, so first of all, what is the problem if we just go ahead and leave out the data? That's not going to work. So in the homework, there's a homework problem to, let's just zero out every other line. So here's K-space. So what if we just, what if we just block out every other line? So just like zero every other line. A lot of times we can sort of say that we're zeroing it by just making a dashed line. So start with a Fourier transform of a brane, and then leave that line, take out this one, leave that line, take out this one, leave that line. So what happens if you do that, you'll see you'll immediately have the field of view. You'll get these ghosts that will sort of like move down, like half of the field of view down. So it looks like you got another copy of the brane that's displaced on top of your actual copy by half of the field of view. So if you look at that, obviously that's not going to work. You just can't leave it out. And when you first think about this, remember when we talked about the correlation between different spatial frequencies, we said that that the Fourier transform is an orthogonal decomposition. What does that mean? It means that we're sort of decomposing this brane into these different spatial frequencies, each of which is orthogonal, meaning uncorrelated with every other one. So of course it makes sense if you leave out some of the data, that data is completely, the data in this line of K-space completely uncorrelated with the data in another line. And so so clearly you're just leaving out, there's no way you're not going to have a problem, because you've decomposed the data when you take a Fourier transform into these statistically independent data points. Each frequency is completely uncorrelated with each other frequency. So when you first hear this, like, how could we possibly interpolate here? Because we don't know what to really interpolate, because it's completely independent information in each line. And so that's what this does. When you have coils like this, it allows you to essentially smear the spatial frequency data out into different frequencies. Very, very counterintuitive, but here's how it works. So if we start on this side with the image, so this is convolution in one domain is the same as multiplication in another domain. And so here's the image side of things. And so, and then here's the spatial frequency side of things. So that's after we Fourier transform. So what is our brane? Well, we're going to use our regular brane, which is a cosine. Doesn't look much like a brane, but it has the advantage of that we understand how it works. So here's a 1, 2, 3, 4. So there's our cosine brane. So this is our brane. Not a very good brane, but it's a brane that we can take the Fourier transform of very easily. So what's the Fourier transform of that? So we can go back and forth. If we ft that cosine, then what we get is 2 spikes, like that. So this is spatial frequency. This is space. So So now what happens when we have a coil like this? So if you have a coil like this, what is that? That's actually multiplying, not adding, sort of multiply. So multiply that by the coil fall-off function. So this is, so here's our brain, here's our coil fall-off function. And so what does that look like? Well, it sort of looks like, it doesn't look exactly like a Gaussian, but let's just say it sort of looks like a Gaussian. So when we multiply that, what is that equal to? So it's going to equal, so not adding it, so multiplying it. So it's what it's going to be equal to is that Fourier, that cosine in kind of a Gaussian envelope. So it's going to look like that cosine. I got to put the peaks in there so I can get this correct. So it's going to look like something like, like this. Okay, so that's our brain image. It's not a very good brain, but it's only got one frequency in it, but it's our brain image. With a bright spot. And where's the bright spot? Like in the middle of the coil. Bright spot. So like, here's the bright spot right there. And that's, like right in the middle of the coil. Okay, so that wasn't very informative so far, but now let's just go over to the Fourier domain to see what it's doing over in K-space. And so first of all, what's the Fourier transform of Gaussian? Well, it's basically a Gaussian, but it has the property, remember that whenever you do the Fourier transform, what you're doing is each point in one domain maps to all the points in the other domain and vice versa. So all the points in this domain will map to every single point in the other domain. And because of that, it has this sort of strange property where if you look at something like a Gaussian, if you make the Gaussian narrower, the Fourier transform of it is wider. Or, if you make it wider, the Fourier transform is narrower. So it's going to be a narrow Gaussian over there in K-space, so spatial frequency space. And so now we're in the other domain. So instead of multiplying, we convolve. So what happens when we convolve a Gaussian? Like this is your Photoshop filter. So here's your Photoshop image. It's just got two spikes in it, and you convolve it with a Photoshop filter that is like a narrow Gaussian. What is it going to do? Well, it's just going to basically blur out those spikes. And so what's going to happen is where the spike would be, instead of a spike, now you'll have like a little mini Gaussian like that. And you'll have the same thing for negative frequency space. So there'll be another negative frequency spike there. Okay, but now what's happened? So if we take the inverse Fourier transform of this, so it's important to keep in mind that this is not blurring the image. I kind of like had a little sort of mental garden path mistake on that. It doesn't blur the image. Let me go this way. We've blurred the spatial frequencies of this original signal, which just used to have just two little spikes in it. We haven't blurred the image. All it does is it just makes an image with a bright spot. It makes a sharp, so this is a sharp, not blurred, brain image. Brain image with a bright spot. So But what have we done in K-space? We kind of smeared out the data. So it smears frequencies from original one freak brain. So we had our stupid brain that just that only has one spatial frequency in it over here, and so we kind of smeared it out into the adjoining frequencies, adjoining spatial frequencies. Okay, so now that doesn't seem to help too much, but the important point is that this, so, what are the take-home points? So the first take-home point is that, K-space blur. So we moved spatial frequencies over. But remember, doesn't blur image. It just makes a bright spot. So it doesn't blur image. It just kind of smears the spatial frequencies into nearby things. When we inverse Fourier transform this, we get something that's sharp, just as sharp as this original cosine. You can see all the bumps in it, but it's got a bright spot. So that's the first thing. But the second thing, so that's the first important point. But the second thing is we can use the same argument for all frequencies. All spatial frequencies. So I just did one cosine brain, but the brain consists of all different spatial frequencies. It consists of spatial frequency 4, 5, 6. There's a lot of 1, and so we can apply the exact same. And the same amount of blurring will occur. That's the important point. So it's the same argument. So the width of this blur at all these different frequencies is exactly the same. So what does that suggest? Well, it suggests now we've got a way to interpolate those missing data points, because some of the frequencies have been sort of smeared into the adjoining frequencies. And so the way that you do this, there's a bunch of different ways of doing it, of trying to reconstruct missing data. And I'll just talk about one. So there's one called GRAPPA. That's the one I'm going to talk about. But there's another one called SENSE. And one of the Friday lectures, I talked about general linear inverse. All of these things, rely on smearing of originally orthogonal frequencies. What's causing this? What's causing this is coils with low spatial frequency bright spots. So all you need to do this is just coils that just have something that sort of doesn't record uniformly from the entire brain, and it just has like a little bit of a bright spot. It doesn't have to be like a sharp bright spot. In fact, it's not good if it's a real sharp bright spot. It's better if it's just kind of like a very gentle bright spot, like a little more from here versus a little more from here. So that's what's actually causing this, this smearing to happen. And because of that, then we can do these reconstruction methods that rely on the fact that now it's kind of been smeared out to the surrounding guys, and so there's some information in the surrounding guys. And so how do you do this? We'll just give the example for GRAPPA. So how you do it for GRAPPA is you first record all the lines of K-space. So record all the lines of K-space. usually what they do is just record all the lines right in the middle of K-space because that's where the signal is the best. So for the first scan, if you're doing GRAPPA, is record all the lines of K-space. You can leave the ones out here. So I'll leave those guys blank, the higher spatial frequency ones. But right in the middle, record all the lines. And like I said, why the middle? Well, because that's where the banks, that's where the money is. That's where the big signal is. So this is, all lines, K-space in middle, and high sig middle. Then what we can do is take that data and attempt to predict the missing data. So we can take that data like this, and then what we can do is we've got all the data there, and so what we can do is essentially try to predict the missing data. So here's some surrounding frequencies in K-space, and so all we do is we make what's called a GRAPPA kernel. But what is that? It's basically just training you to recognize what that point is based on the surrounding data points. So here's the surrounding data points like that. Now we actually know what it is because we recorded it, and so then we can say, like, given these surrounding data points, what do we need to do to those surrounding data points in order to predict this point which we've actually recorded? And it turns out that GRAPPA kernel, because of the argument that it's the same argument for all spatial frequencies, you can use that same GRAPPA kernel across different parts of K-space because the blur that's occurring in spatial frequencies is the same in different parts of K-space. And in fact, you have even more data than just this one slice, because we've got another slice over here, and from a different coil, and that different coil slice, we can do the same thing over there. And so what we can do is we can take that same point and try to predict what that point should be from the other slices too. So this is, another coil K-space. This is, one coil K-space, because, the coils are on at the same time, and so we're getting a full K-space for every coil. And so not only do you have the surrounding lines, which have got some information from, every spatial frequency in them, but you also have multiple coils. And so basically what you can do is you can essentially interpolate, sort of intelligently interpolate what the missing data should be on the basis of the surrounding lines, which normally would be completely orthogonal. The spatial frequencies would be completely orthogonal, but because of this very low spatial frequency coil fall-off function, which Fourier transforms to a teeny little Gaussian, which we then convolve with each frequency, it kind of smears out the data. And so when you're recording with a coil with a sort of a smooth fall-off function, what it's doing is it's kind of, instead of recording a point in K-space, it's almost like you're recording a little smear in K-space that's going across K-space. And because of that, then we can sort of intelligently reconstruct missing data points. And so then this is a big speed up, because, we only collected half of the data. So we essentially just skipped every other line of K-space and then just filled it in by taking our first scan where we collected every line of K-space. So hopefully this argument makes a certain amount of sense, that that having this smooth coil fall-off function, gentle coil fall-off function, Fourier transforms into a little spiky little Gaussian, which smears some of the data in K-space and then allows us to reconstruct missing data after we've left some out, assuming that we've got an actual sort of initial image that has a full recording of K-space so that we can train this thing. So we can train the predictor that will fill in the missing data points. So all of these methods, GRAPPA, sense, which is kind of like a general linear inverse, or just doing this whole thing as a linear inverse, wouldn't work well if it weren't for this, the fact that that the data has been smeared. And what's causing it to be smeared is kind of counterintuitive, but it's a very gentle fall-off function that extends across, the whole brain, basically. Very low spatial frequency fall-off function. Okay, so is that so if you can go and try to read a paper on GRAPPA, and you'll see it's a little confusing. It can be a little confusing, but now this is widely used. So every single day at the scanner, we do an MP range with GRAPPA turned on, and only record half of the data. And that's a big difference, because now we get a scan in 5 minutes that used to take 10 minutes, and it looks ever so slightly noisier, but basically it's just fine. And so it's just like overnight, just doubled the rate of collecting data. So it's a big effect. Okay, any questions about GRAPPA? I can't remember what GRAPPA stands for, but it's just this method of interpolating the missing data in K-space. So you can see, like, the more coils, because you can use all these coils, the more coils you have, the better. And so we have like 32 or 64 channels of coils, so you'll end up with 64 K-spaces. And so you can use 64 K-spaces to predict, 1 point. So that gives you a lot of redundancy. Okay, any questions about EPI or GRAPPA? And so next time on Friday, we'll talk about multi-band, which is kind of applying GRAPPA in another twisted way to multiple slices excited at the same time, but it's kind of the same idea. Okay.